Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solving problem number 17. Let's consider this network consisting of 5 resistors labeled R1 through R5 as well as 3 independent voltage sources VA, VB and VC. The question now is to calculate the value of Vx using Thevenin's theorem. Vx is the voltage across the resistor R4. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. In our example, RTH is connected in series with the R4, which plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit and disconnecting the resistor R4, which means the voltage sources will be replaced by a short circuit. The Thevenin's resistance represents the equivalent resistance between terminals A and B. That means RTH is equal to the parallel combination of R1 and R2 connected in series with R3 in parallel to R5. And I will consider RA is equal to the parallel combination of R1 and R2 connected in series with the R3. That means RA is equal to R1 times R2 over R1 plus R2 plus R3. And if we replace the resistors with their numerical values, we obtain RA is equal to 42 ohms. That means RTH is equal to the parallel combination of RA and R5. Therefore, RTH can be calculated using the following formula: RA times R5 over RA plus R5. And if we replace RA and R5 with their numerical values, we obtain RTH is equal to 8.07 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage calculated between terminals A and B when R4 is disconnected. To find the open circuit voltage VOC, I will apply the mesh analysis method. And I will consider this mesh 1, and this is mesh 2, and this is mesh 3. And I will consider also I1 is the current in mesh 1, I2 is the current in mesh 2, and I3 is the current in mesh 3. In mesh 1, we can write, by applying Kirchhoff's voltage law, negative VA plus R1 times I1 plus R2 times I1 minus I2 is equal to 0. And if we replace the resistors and the voltage with their numerical values, we obtain negative 10 plus 50 times I1 minus 30 times I2 is equal to 0. Now, by applying Kirchhoff's voltage law in mesh 2, we can write R2 times I2 minus I1 plus R3 times I2 plus VOC minus VB is equal to 0. And if we replace the voltage and the resistors with their numerical values, we obtain negative 30 times I1 plus 60 times I2 plus VOC minus 10 is equal to 0. Let's move on now to mesh 3. By applying Kirchhoff's voltage law in mesh 3, we can write negative VOC plus R5 times I3 minus VC is equal to 0. We know here that the terminals A and B is an open circuit. That means the current flow in this direction is equal to 0. From that, we can conclude that I2 is equal to I3. And if we replace I3 with I2 in this equation, and we replace the resistor and the voltage with their numerical values, we obtain negative VOC plus 10 times I2 minus 10 is equal to 0. Now, by performing 2 plus 30 over 50 times 1, we obtain 42 times I2 plus VOC minus 16 is equal to 0. And now, by performing 4 minus 4.2 times 3, we derive one equation in terms of VOC. That means VOC is equal to negative 26 over 5.2. We get VOC is equal to negative 5 volt. From here, we can find VTH is equal to VOC is equal to negative 5 volt. Now, in order to calculate Vx, I'm going to use the voltage division rule. That means Vx is equal to R4 over R4 plus RTH times VTH. And if we replace R4, RTH and VTH with their numerical values, we obtain Vx is equal to negative 4.16 volt. After completing the calculations, I performed simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our networks drawn in SPICE simulator. This is the original circuit, and this is the Thevenin's equivalent circuit between terminals A and B. I connect here a voltmeter in order to measure the voltage across the resistor R4, and here also I connected the voltmeter in order to measure the voltage across the resistor R4. Let's move on to analysis. They say analysis, calculate nodal voltage. We can see here that the voltage Vx across the resistor R4 is equal to negative 4.16 volt in the original circuit and is equal to negative 4.16 volt in the Thevenin's equivalent circuit. From the simulation, it becomes clear that the voltage Vx is similar when using both the original circuit and the Thevenin's equivalent circuit. This similarity validates the correctness of our calculations. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time, another video about Thevenin's theorem. Take care and bye-bye.